Let's look at a practical example for solving these ODEs. And this comes from physics, kind of the popular ballistics equation, or a ballistics type of problem where we're going to be launching a cannonball into the air and we want to know how far away from the ground, or from where we start, is it going to land by the time it hits the ground. So if we were in physics class, we would come up with the free body diagram for this situation, or if we were in a dynamics class, and with the free body diagram, we would be able to come up with what the ordinary differential equations are that are going to determine the trajectory of this cannonball. So if we sum forces in the y direction or the vertical direction, we sum forces in the x direction, we would be able to come up with a relationship for x double dot, which is the acceleration in the x direction, and y double dot, the acceleration in the y direction. So we are going to come up with these 4 state variables that we're going to need. Since there's an x double dot term and a y double dot term, we're going to need 4 state variables to solve this: y, y dot, x, and x dot. And from the free body diagrams and writing the sum of forces, we'll be able to come up with definitions for x1 dot, y dot, y double dot, x dot, and x double dot. So the first thing we want to do is create our function for these state variables. So don't worry too much at the moment where these equations are coming from. I'm not going to go through all of that, but if we went through all the physics, we would get these 4 equations for our state variables. So I'm going to call this ODE for EX3A. And this will take time. I will call my state variables collection X again, and G. I'll add a third argument to this, which will be the value of gravity that we're going to use. That way we can see how to use these extra arguments in here. All right, so I want to pre-allocate. I have 4 state variables I need. So I need a column vector with 4 values in it. And then I have to fill them in. All right, so x dot 1, which is y dot, is going to be the same as x2. X dot 2, which is y double dot, this is going to be the acceleration in the y direction. Well, that's negative g, because the gravity is going to be pulling it in the negative y direction. X dot of 3 is going to be x4, and x dot of 4 is going to be 0. The acceleration horizontally in this example is 0. We're ignoring the effect of air resistance. Alright, so we have all 4 of the derivatives of our state variables now defined here. Here it's giving me a red here. It's warning me that none of these are explicitly functions of t, like we did see in the previous ones. We can ignore that warning. It's not going to really hurt us here. Alright, so now we want to go and solve for the x position and the y position. Again, this physically now will have some meaning to us, because this will tell us where is the cannonball over time from when we launch it to when it hits the ground. So we use ODE45. And here our function is ODE for example 3a. That takes t, it takes x. You see it popped up here. It also takes a value for gravity. I'm going to use a value of 9.81, and we can see how it's different if we launched it on Earth or on a different planet, how it would be affected. And we don't know how long we want to run it. What we're looking for here is how long it takes to hit the ground if there's no air resistance and under these initial conditions. So at the moment, I don't know how long that's going to take. I'm just going to run it for 30 seconds and kind of see what happens. I can always kind of bring this back a little bit. And I have to give it the initial conditions. We have 4 state variables, which means we're going to have 4 initial conditions. So I need the initial values of x1, x2, x3, and x4. And remember, from the mapping that's on the slide here, we need to make sure that they're in the same order. So x1's initial value, that is the same as what's the initial height of the cannonball. In this case, it's initially 10 meters off the ground, so the first value is 10. Then I want to know the original value, the initial value for y dot. So it has to be its velocity in the y direction. In this case, we're launching it at 20 degrees from the horizontal with a velocity of 53 meters per second. So in the y direction, that's going to be 53 times the sine of 20 degrees. That's how much of the velocity is just in the y direction. Right. x3 is x, the horizontal position. Now initially, that's going to start at 0, because that's how we're just defining the initial x is at 0, and then as it goes to the right, it's going to increase. And then x4 is the initial value of x dot, or the velocity in the x direction. That's going to be its velocity times the cosine of 20 degrees. Close the rest of that out, and we can run this. Alright, so here I want to see what is the cannonball doing as it goes through the air. So I actually want to plot here. It will be a version of the phase plane, or the phase portrait. I want to look at the horizontal position of the ball. That's going to be the third column of x, the x3, versus y, which is the first column. So I have x, my y label here is going to be y, and I want a grid here. Alright, so again, I am plotting the horizontal position of the cannonball versus the vertical position of the cannonball. And nowhere here explicitly do I see time, but I do see that pretty quickly it's below 0, and all of this would be simulating it falling through the Earth. So 30 seconds is way too long to run this to see anything usable here. If I only run it for 3 seconds, I see it doesn't hit the ground yet. Alright, so 6 seconds, we actually here see that it hits the ground and kind of goes through. So for right now, I'm just going to leave it at simulating it for 6 seconds. So we know it can't go through the ground. Once it hits 0, it actually would stop, and we'll get to putting that in a minute here. But we see here, we fire it at 10 meters above the horizontal. It starts to travel, and then gravity takes over, and then it starts to fall back towards the Earth, and then around here is where it hits the ground. So what I want to know here, based on the simulation, based on the data, I want to know how far does it go before hitting the ground. So how far horizontally does it go? By eye, it looks to be around like 210 meters. Because again, here, all of our initial conditions were in meters or meters per second. But I don't want to just eyeball this. I want to get, from my simulation, a little bit better idea of what's happening. I'm going to use more points in my simulation here so I get a little bit better results. Right, so from 0 by 0.1 seconds to 6. Actually, I'll do it by 100th of a second to get a little bit more resolution here. Right, so what I want to find is, when does it hit the ground? So based on the data I have, I can find the answer to that, because I can say, when's the first time that the value of y, which I'll just assign that value here, which is the third column of x. So I want to find, when is the value of y first less than or equal to 0? Again, this is going to be an estimate because it's not actually going to be equal to 0, or very unlikely to be equal to 0 at any point, but I want to know when that happens. Okay. Oh, sorry, that is not, I actually want y to be the first column, not the third column. Okay, that works better. And I don't care about all the times it's less than or equal to 0, I just care about the first time that happens. So it first happens at the 420th index. So I will call that hit ground. Alright, so if I want to know the time that it hits the ground, I want to know, using that index, the 420th value, what's the 420th value of t? So it says that at 4.19 seconds is when it hits the ground. Again, more or less equal to that. So let me actually go back up here and tighten this up a little bit more and only go to 4.3 seconds because it says that it hit the ground already by 4.2 seconds. Alright, so we see it does go a little bit past, but it does tighten this up quite a bit. Also what we can do is I can make my axes to scale. Since they're both in meters, if I do axis equal, now we see that the scale is the same in the horizontal as it is in the vertical, and now it makes a little bit more sense because the scales are equal. So it goes a lot further than it goes up and down, which is to be expected if we're launching this cannonball. Okay, but get back to what we were looking at here. So the time it hit the ground, 4.19 seconds. Again, by reducing this even further, I can get a little bit better of an estimate. So if I now do it by thousandths of a second, its estimate is 4.184 seconds is when it hits the ground. But really what I'm looking for is how far horizontally does it travel before it hits the ground with no air resistance. So again, by eye, it looks around 210, but I can get the exact value since the third column of x is going to be my horizontal position, and I just care about the index where it hit the ground. So if I run just that, it says that at that index, which here is the 4185th index, at that index it had an x value of 208.3787 as its value. So that's how far horizontally the cannonball traveled before hitting the ground. So again, to recap what we looked at here is we started with the ODE of this system, or the ordinary differential equations of the system that we got from physics. I'll skip over that part. But we saw we have four state variables, y, y dot, x, and x dot. So I had to make the driver for that, I'll call it. So I had to define what is x1 dot, x2 dot, etc. And then run the solver, the ODE45 here. I did kind of refine in here what my time scale was, but I started out at 30 seconds and kept bringing it in as visually I saw that it hit the ground well before 30 seconds. I had to put in my initial conditions. So initially y was at 10 meters with a velocity of 53 sine 20 meters per second. Initially x was 0, and the x velocity was originally 53 cosine 20 meters per second to the right. I then can plot what it looks like. Here I have it to scale. So as it travels through the air, what's happening here? I can take this in just a little bit more and refine this a little bit. So this is what the cannonball would look like as it's traveling through the air. That's the x versus the y value. And then I wanted to know when it hit the ground. So I wanted to find when was the first y point that was below 0. So I used the find command for that. So it happened on the 4185th index. So the time at that index when it hit the ground, 4.184 seconds, and the x value when it hit the ground, 208 meters